Okay. Yes. Okay. Good morning, class. Before we start our lesson on determining the deformation of beams and frames, let us have a recap of what we have learned last week. Okay. Last week we have learned on how to analyze beams and frames. Okay. Here I would like to recap on the procedure. Okay. On how to analyze beams and frames. Okay. If you still remember, we use the methods of cut section. Okay, so we need to identify when you have this problem, okay, where to cut a section, okay, to determine the internal forces. Okay, so we have gone through several examples on beams and frame. Okay, once we have identified the position or the range of the section that we want to cut the section, okay, then we will proceed, okay, on drawing the free body diagram. Okay, for example, just to as a revision, for this case, okay, can you see my slides? Example 4.1.
Yes.
Okay, so
Of course, madam.
how many sections we have cut for this example? You still remember?
Four.
Four.
Thank you, thank you. Okay, so yeah, we need a tips before. We need to cut a section at least once in a member. Okay, now we have three members here: A, B, B, C, and C, D. Okay, so at least one. Okay, but it will be more if you have differential in terms of loading. For example, in member AB, you have this point load 15 kilonewton. Therefore, before and after the 15 kilonewton, we need to cut sections because we know that the shear equation or bending equations, okay, due to these loadings may not be the same. So therefore, AB, we will cut two sections. Okay, in BC, we will cut only one section. This is because the distributed loading, whether it is in the uniformly rectangular shape or in the triangular distributed loading, these types of loading can represent by only one loading equations. Therefore, you only need to cut once in these types of loading. Okay, so at BC, we are going to cut only once. And at CD, we need to cut once is because this is another new member. Okay, and the internal forces will be definitely different from the other members. Okay, because of this arrangement as well. Okay, so after we have decided on this cut section earlier and also CD, it's not drawn here, then we start to draw this. This is a free body diagram. Oops, I need to click my pen first. Okay, this is the free body. Okay, diagram. Okay, when we want to draw our free body diagram, okay, we need to decide, okay, where to analyze our section. If you still remember when we cut section, we cut a structure using the method of section. This structure will cut into two parts. For example, if I'm looking at this 1-1, so now this frame, when I cut into at the section 1-1, it become either this part or the other part like this. Okay, so you need to put in all the loading, all the support reaction, and all the internal force at the section you want to analyze. Either this part, let's say number 1 part, or a left part, or the right part, or number 2, part 2. Okay, so this is what been chosen. For example, I'm in this case, part 1 has been analyzed. So you need to draw all these. Okay, there is support reaction, the internal forces following the positive sign, and then you need to decide on this X, where you want to start the X. Okay, so we have tried also several positions to get the X start with. Okay, but in this case we start at A. Okay, So now if you start at A, so A is actually 0 meter you measured, okay, the distance. And you also need to know how to name this section, okay, and this range. This range is very important in this lesson, okay, because we are going to use it, okay, for some of this calculation, okay, and it is specifically important of this X. Wait now, episode is training. Okay. Okay, so this range is depends very much on where you start your X. Okay, so for example, here is before the 15 kilonewton. These sections will be start from 0 to 2 meter. Okay, then we start forming these shear and bending moment equations by using summation Fy and summation MA. Okay, previously we have been arguing on whether we shall put a summation Fx in this case, because now you are dealing with Ax. Okay, just to make sure every members of the frames are using, when shear force is using summation Fy, we use this so-called a local axis, okay, to decide on this direction. Okay, maybe I will clear this board and explain a little bit on the local. Okay, this is PDF. Cannot be erased. So maybe I use these slides. Okay, for example, when you talk about this coordination, we will talk X, Y. For this 2D structure, this will be the global axis. Okay, X and Y. Everyone know when taking summation Fy, all the loading that deal with this or Y direction or vertically, okay, in your system. So this is global. Okay, global Y positive, global X positive. Okay, but when we talk about local, local means this X will be placed always to your member, parallel to your member. For example, in this AB, the member is running, if it is in global direction, it is running vertically. But now at the local axis, you put your X in such a way. So meaning that any dimensions or loading running here is considered X. Okay, this is local, and this will be the I'm drawing another. This perpendicular to this member will be the y-axis. Okay, so once you place your eyes here, you are looking at the vertical is positive in going to your left. Okay, therefore you can answer here. You are always using summation Fy when you are dealing with shear. Okay, because when you cut a section here, the shear is running at this local y direction. Okay, similarly, when you playing around with this BC, this X will be running this way and the Y is running this way. So when you are taking summation Fy equal to 0, all the loading at this Y direction, okay, will be considered in your summation Fy equal to 0. Okay, so then last lesson, we also determine shear force and bending moment from these shear and bending equations, okay, at all these specific points. How to substitute? Okay, when we have this equation, let's say, that has this x value. Okay, so we just substitute the x value inside this equation. Then we can get the specific point of that shear force. Okay, and we also know that how to determine the inflection point of a bending moment in your in order to draw your shear force diagram, or to indicate where is the ultimate or maximum moment at that particular member. Okay, how to do that? Anyone can help? If we already have this shear force equation, how to determine the inflection point for moment curvature.
V is equal to 0.
Thank you very much. Okay.
Welcome,
Here we are.
madam. I got you.
Yeah. Yes. Yeah. We need to take this V equal to 0 because this inflection will happen, okay, when V is equal to 0. So once we have these equations of V, we just put it as is 0. You can get this X value. This X value is the distance, okay, they indicate, okay, the occurrence of this inflection point, where you later substitute the X, okay, into your bending moment equation. Then you can, sorry, it's here, bending moment equation. Then you can get your inflection point, okay, immediately. Okay, so we also look at how to draw the this bending moment shear force diagram from our these equations. Okay, so this is what we have learned last week. Okay, but this week we are going to go further. Besides of we want to know about these internal forces for our design, we also need to limit our structure with certain deflection. We do not want this structure to deflect so much that it is uncomfortable, okay, or it may result in a failure of a structure. Okay, but of course, the limitation or allowable of the displacements will be guided by this certain of this code of practice or standards when you learn your design later. But now, in this course, our concern is to determine exactly or actually what is the deflection at certain point. Okay, so this is our lesson today. I'm going to close this. Okay. Can you see my slides? What is the title of the slide?
Virtual work method. Deformation.
Okay, thank you very much. I hope you get these notes. Okay, there is 2 examples in there, and that if possible, we are going to do exercises after my explanation. Okay, to just make sure you understand more on how to apply this virtual work method. Okay, I shall delete this. Okay. Okay, the virtual work method has been explained, okay, or in your reading material in our week 1 lesson. Okay, so if you want to understand more about virtual work method, please refer back to what we have learned in first week. But today we are going to directly use this virtual work method for the beams and frames, and it is different. Okay, it is different from the truss analysis. But I'm not talking about the concept. I'm talking about the equations used, because if you still remember the truss, we do not have any bending moment, and we deal always with axial force, either it is compression or tension. Therefore, when determining this deflection, if you still remember, we are using axial force. Okay, but in these beams and frames, the significant internal forces, okay, will be moment, bending moment. Okay, so we are going to use moment right now, okay, in our calculation. Okay, so again, this moment, there are 2 moments. Maybe you already can guess what is a small m and the big M here means. Okay, and then just go back again for those who have already forgotten. The very important, okay, principles in this virtual work is you need to make sure that whatever done externally, okay, must be reflects internally. Okay, this is the principle. Okay, the main. So now let's have a look on this virtual work for beams and frame. If you can see that we have two equations. Actually, this is the same. If you look at that, this is m, small m, big M, and this is small m, big N. Okay, but why this deflection is in terms of different symbol? Anyone can help? All right, this theta is a rotational displacement or deformation. Okay, deformation. Okay, so this delta is a translation. Okay, these units will be in radian. These units can be in mm or meter. Okay, so I will just put mm here. Okay, you can convert into meter. Okay, so this is a very old centimeter. This will be very worldwide used. Okay, SI units. Okay, for rotation, if you still remember, if this is a simply supported beam. Okay, so this is in our week 1 lesson. Okay, to know where is the what is the degree of freedom, if you still remember. Okay, so for example, in this A, okay, may I know what is the available deflection at A, which means the displacement is not equal to 0. Anyone can help at A? Okay, just the tips. In this 2D analysis, we will always have translation. Okay, translation displacement where we have in global delta x. Okay, we have in terms of vertical delta y, and also in terms of rotational. Okay, so here at pin at A, okay, which displacement is not equal to 0? We have only these three: delta x, delta y, or theta. Oops. Am I out from the group? Let me check. Oh, I'm still in the group.
I don't know, madam.
Okay.
I don't understand the question.
Yeah, okay, all right. So again, maybe I will help in this pin. Okay, at A. Okay, my question is, at A, it has been restrained. Okay, in terms of X and Y direction. If you look at these supports, okay, we have a AY and AX. This is a support reaction, which also means that this point A has been restrained from movement, cannot move at all. At which direction? At X direction and also at Y direction. Therefore, at this A itself, X is equal to 0 and Y is equal to 0. We know that it cannot move at that direction, but it can have a rotation. When you draw your bending moment diagram or deflection curve, you draw in such. So there is a rotational, which this beam is actually deflect, okay, in such a way. This we call a rotational displacement. Do you understand what I mean now?
Yes, yes.
Yeah, I'm talking about displacement right now. Okay, because we want to determine the displacement. If you do not know about this displacement, so you never know what you actually want to determine. Okay, so I'm drawing the diffracted shape of the beam so that you understand on such. Okay, now I want to test you. Okay, on at B. So now we have this support reaction By. Okay, may I know at this B, what is the value of delta X, delta Y, and also theta? So can I have from you delta X? Any value?
0.
How about delta Y?
0.
How about theta? Okay, so theta is unknown. We don't know. We need to determine. There is value. Okay, delta X is unknown. Okay, we need to determine. We don't know the value. Okay, delta Y is 0. Okay, so a very simple tips guide you is whenever got this support reaction, okay, like for example by at that direction, meaning that at that direction is restricted from movement. It cannot go at y direction, okay, unless that support settle. Like for example, this support B settle 1 mm, then of course it will deflect 1 mm because of the support settlement. But now if there is no support settlement, the B cannot move down, whatever reason. Okay, so but it can move because this is a roller. It is not being restricted in bx. Okay, therefore this roller can move to other position. Then we will have a delta x here. Do you understand what I mean?
Yes.
Yeah, and this delta x is unknown. We don't know what is the value, and we can determine, okay, from virtual work method. And of course, because this is simply supported, I'm drawing another part of this deflected shape. Okay, so now if you can see that we also have a rotational displacement at this B. Okay, and of course it is unknown. Okay, we need to determine it. So whenever you want to determine this theta, you use this equation. Okay, if of course it is the same, but I'm going to let you know later what is the how in the procedure how to get this theta done. Okay, and to get the delta x or delta y, you use this equation. Okay, so now let us have a look on what is this. It is being the no gap for this. I hope you can read. Maybe you can help together. So external virtual unit load acting on the beam or frame in the direction of delta. Okay, this is one. Okay, later we will see the illustration. Small m is the moments, okay, for the caused by the virtual unit load, okay, or it happened at the from the virtual structure. Okay, delta is the external displacement, okay, caused by the real load. Okay, this is what we want to determine. Okay, either this delta or this theta. Okay, different name. One is the rotational, one is the translation. Okay, big M is the moment, okay, of the beam or frame, okay, by the real loads. Okay, then we can say that this is from real structure. Okay, then of course we have a material properties and sectional properties here. E is modulus of elasticity, and I is a moment of inertia. Okay, if I would like to play back the earlier in the truss, okay, what we use A and E. Okay, so be careful. I saw quite numbers of students. Okay, when they write this equation, they put the wrong this material and the properties. So for beams and frame, the material and sectional properties they address is EI, and for truss is AE. Okay, so be careful. Okay, so now let us try on this one of the very simple, I would say, because one span only. And this is a cantilever beam. You need to be able to classify this as well. This is cantilever beam. Why? Because we have a free end here. And this must be fixed. Okay, be careful. Okay, so now let us start to determine the deflection at B of the beam. So the problem is we want to determine deflection where at B. Okay, so just to recall earlier, we are going to have two structures to analyze. Okay, analyze for what? Analyze for in bending moment. Okay, we do not require shear force in this case for the calculation, and also the axial force. We only require bending moment. Okay, and now EI is given to you. Let's try. Okay, so I have put everything here. Okay, so maybe I can put this slowly. Maybe not that fast. That is okay. Okay, so let us try to analyze these two structures. I will have two structure in the virtual work method. So first of all, you can call this primary or real structure. Okay, where do you get this real structure? You just get directly from your problem. Okay, first of all, you need to make sure this is a determinate system. What is the equations? N minus R minus N minus C. Okay, so R is a support reaction. We have three here, AX, AY, and MA. And then N is always 3, and then you have 0 because there is no hinge here. So this beam is a statically determinate beam. Okay, then you can use the virtual work method. Okay, so this virtual work method you have to produce the two structures. One is the real primary structure. We also can name it the big M here, and another one is the virtual structure. Okay, where we name it a small m here. What is the characteristic of the virtual structure? Just to recall, here we have a tips here. We remove all the real load and we apply 1 kilonewton at, oops. Can you help me to correct this? At B. Okay, so actually I'm not sure they how what is the what is the next question or solution for this. But when you place this 1 kilonewton at B vertically, meaning that you are actually determine a vertical, okay, displacement at B. Okay, remember this direction of this arrow show the direction of the displacement you want to determine. If you want to determine horizontal displacement at B, you place your 1 kilonewton here horizontally. Okay, but of course, this is not your concern right now. Okay, so be careful. First of all, in this virtual structure, you can draw everything from the real structure, okay, to create your virtual structure. Oops, wait, there's somebody joining. No, Shafika. Okay. All right, so let's continue. Okay, so where am I right now? Okay, so now once you have copied everything to your virtual structure from the real structure, you remove all the real loads. Don't draw it at all. Then you apply 1 kilonewton at where you want to determine the displacement. So now you want to determine at B. So you put your 1 kilonewton at B, and the direction must be follow whatever you want to determine. For example, you want to determine vertical displacement, so you put the arrow vertically. Okay, so now we can just go back to our last week lesson. Okay, we need to determine the internal force. Okay, in this system, how many cut section we need to draw? I mean, we need to cut this system into how many sections? AB? Yes, thank you. You only need to cut once because this is UDL. Okay, so we only need to provide once. So then we can start on writing. Okay, so we can, if you can see that I have put it in a table. Okay, so if you don't want to put in a table, no problem. It just make me easier for me to explain. Now I have decided to analyze only my right part. Okay, so I can draw my free body diagram in such. Okay, for this primary structure, this is B, and I start it from X. Start X from B, and then this is my cut section, and I only one moment. Okay, the shear force, of course, and axial force also can draw, but my concern is only moment. Okay, so now I only draw moment. So now this is my UDL 12 kilonewton per meter. Okay, so the range for this section, okay, I can call this BA because I start from, okay, B. Okay, and then my X range from, because now I'm talking about BA, I'm representing these equations for the whole length of my BA. Therefore, it should be start from B, which is 0 when you measure from B, and the maximum length will be 10 meter. Okay, so this will be your range. You need to be able to write your range. Then the next one is just to determine your bending moment. Okay, equations. So you can take a summation moment, okay, equal to 0. You put a, let's say, clockwise. Okay, so this 12 kilonewton per meter can be represented, okay, by a resultant force by using this area of this rectangular, which is a 12, and the x is the distance. Okay, so we have 12x, and this 12x is acting at halfway, okay, half of x. So this is x over 2, and this is clockwise, positive, correct? And then the moment also positive. Okay, this is how you get it. So your moment is 6x, am I? 6x squared, negative. Yes. Okay, so this is how you do it. Are you okay, class?
Yes.
Yeah.
Okay. Yes, thank you very much. If you are okay, can I go a faster way in solving this without writing this? Okay, so I'm going to erase this and try again. Okay, now if you are okay, you can't directly draw this. Okay, but my pen cannot go out. Okay, anyway, oh, but I can put it. Okay, because now you want to do it in a fast way, because you have a very long process. Okay, you might want to try this. Okay, so this is just similar to what you have practiced just now, but now you just directly solve it in your diagram. Okay, for example, now you are talking about I want to analyze this. This is right part. Okay, so meaning that now you already forget about this. This is no more in your concern. Okay, you just imagine you are looking at this part only. Yeah, I hope you can understand what I mean. Okay, the rest it's not in your is hidden. Okay, no more. Okay, now you can directly put it, this is your M. Okay, then this is your loading. Okay, so you can directly put in your M is actually equal to So now this is a resultant force, okay, which is 12x that you already know just now because you put your x starting from B. Okay, so the tips is if the loading that will contribute moment to x, this is x, okay, is acting, maybe I write first, okay, if the loading that will contribute to moments at x, okay, is acting same direction, you put it, it will be, it give you a negative value. Okay, if it is acting opposite direction, you treat it as positive value. Why I want to do this is because I want to directly get my moment at the other side and the rest of my loading in the opposite side. Do you get what I mean? Previously, we take a summation moment equal to 0, and then all my M and all other external loads that will contribute to the moments at the same side, and then we equal to 0, right? But right now, I want to straight away putting everything aside from this moment to the opposite side. Therefore, you need to keep in your mind to get this done. Any loading that acting different, the same direction, we have a negative value, and acting opposite direction, we get a positive value. Let's try. Okay, so now this 12x, and then we know that to get the moment, we need a distance. So it will be x over 2, right? So this will be 12x, and the moment is x over 2. Now this moment, 12x, is acting in clockwise, right? So this clockwise, and this moment is clockwise, right? So my tips is if they are same direction, this moment is negative because you are actually dragging to the opposite side. So this is your answer. Okay, and then you skip writing this statement. Do you get what I mean? Hi class. Anyone? I don't understand at all.
Can you repeat, madam?
Okay, I repeat once. Never mind, later we are going to do this exercise. For those who are really cannot accept this, you want step by step because you have established, you can proceed with earlier. But I have to show you this way because I understand that you already go through my last week lesson well. Okay, so it will be good for you to proceed faster. Okay, determining the moments faster now. Okay, so I try again slowly. Okay, and my writing here is not that I don't even can read my own writing well. So maybe you write better in your notes. Okay, now I will write to repeat here. Okay, if the loading that contribute to moments, okay, so what I mean is this loading is about, in this case, is 12x. Okay, other than this internal force moment, the rest of the loads that will give you moments, okay, I intend, okay, these are the other loads, okay, that will be giving moments to x. I intend to bring to the opposite side of my equation directly. I don't want to write this equation anymore here. Okay, so what I always practice is, so if this moment is acting same direction, if they are acting same direction with my this internal moment, I give it a negative value of this moment. If it is acting opposite direction with my this internal moment, I give it a positive value. Okay, of course, later to make sure you understand more, you can practice this once, and then later you practice this. You will get the same answer actually. Okay, so now I go back to how I get this my value here. Okay, so again, so moment is equal to, now I need to get the, this is internal moment, you know. This is this internal moment. Okay, equal to other moment. Now I'm talking about this other moment. Okay, other than this internal moment. It will be, from this case, it will be only 12x. Okay, how to get these moments from 12x? It will be 12x multiply with the distance x over 2. This will be the moment. But now, either you want to put it negative or positive. Okay, so this will be the tips for you. Is that acting the same direction? Is that acting the opposite direction with your internal moment? Okay, so now this 12x, if you look at that, acting about this x is clockwise. So it is acting the same direction with your internal moment, right? So you put a negative value to this moment. Okay, that's all. So you get this negative 6x squared. Can I proceed, class?
Yes.
Okay, yeah, so we will try on this another virtual structure right now. Okay. Okay. So for the virtual structure, we already draw this virtual structure, and please remember for this virtual method, please consider the same side of your cut section. If you start your x from B, you are analyzing this right part. Okay, so for virtual structure, you also consider the right part and start your x from B. And then if you consider your moment acting clockwise as positive, similarly for virtual structure, do the same thing. Okay, because we are going to multiply the m, if you still remember just now, we are going to multiply these two effects later. Okay, so be remember, now I'm going to get this small m done. Okay, again, this is a small m. Okay, I'm going to directly use the methods just now I showed. Okay, so the other loading that will contribute to moment at x will be the 1 kilonewton. Okay, how to get these moments from 1 kilonewton will be 1 kilonewton multiply x, right? Okay, so it will be 1 multiply x. Okay, now this 1 kilonewton is acting clockwise. It will be same direction with my m, small m. So when it is same direction, we have a negative value. Okay, because we are moving to the opposite side. So now you get your negative x value done. Okay, do you prefer this or the previous writing summation moment and continue with the long writing equation? Okay, maybe you are still thinking. Okay, so now I will just proceed. Okay, maybe we will have more exercise later to try, okay, your understanding on this. Okay, but still we don't do anything abnormal here. No. Okay, we just fasten the process. Okay. So next, okay, so we want to use this equation. You know that you are applying this virtual work method. You need to apply this equation. How to use this equation? So we need to have this range written correctly. Okay, so put in the integration because this equation involves integration 0 to 10. And then you put in the small m that you have determined just now, negative x. And then the big M from the real structure, negative 6x squared, and then over EI dx. Then you can use your calculator to solve this delta. Can you help me to try on your calculator whether you can get this 15 power 3? Can you help me? This EI can be putting outside of this integration. Okay, meaning that the EI is outside, and then you have 0 to 10, and then you have negative x and minus negative 6x squared. Okay, or you can directly put this as a 6x cubed into your this calculator. Can you help me to do that? I will be doing the same thing now.
Yes.
Yes.
Okay, anyone cannot get it? Because I remember that there is so many in my earlier class, some has difficulties in getting the answer because they use a different your calculator. I mean the series. Okay, I'm using 570. I have also 350 here. Let me see. Where is my integration? Oh, 350 cannot do. Huh? How about your calculator? You are having a series of what? 300 plus or 500 plus?
500.
500.
Okay, so you can get this 15 power 3
Yes,
without
madam.
problem. Okay, okay. For those who have difficulties, maybe you need to go to the function, I mean Google, and look at the function of how to put in your integration, okay, using the manual of your calculator. Okay, if still cannot, then you can PM me. Okay, then we will search together on how to use your calculator. Okay, but be careful. Sometimes in your problems given, this is not in a exact value. It might in a unknown value like p meter. So if this is so, I'm afraid that you can't use your calculator, but you need to solve this manually. So please, to make sure you can answer this question, okay, in your test uh, happily, make sure you refresh back how to manually solve the integration. Okay, so now I'm going to talk about this. Oh, now it's already 9. Huh? I'm just a bit slow today. So now this, if you look at this, you get 150 mm is positive value. And then it is giving you an indication that this is downward. What does that mean? Why this is positive here value, and it give you indication that this is a downward displacement, deflection.
Follow visual.
Because the deflection going downward, madam? Not like that.
Because yeah, this your answer is true. The deflection that you have found is going downward. Okay, but why you get positive, then you know that it is going downward.
1 km.
Yeah, because of this 1 km direction. Okay, because you have assumed this direction going downward. If you get a positive value at the end, meaning that your assumption here is going downward. But if you get the negative value for your delta B, meaning that it is going upward, your deflection. Do you get what I mean?
Yes.
So yeah, this assumption is very important. Okay, and then your result will let you know whether your assumption is correct or not. Okay, and then after this class, you may want to try, okay, to get this if you want to get the deflection at midpoint of span AB. If you want to get the midpoint at span AB, what you want to do for your virtual structure? If you want to get the vertical displacement at midpoint of span AB,
Change 1 kN position.
thank you very much. So that means you are going to create a new virtual structure, okay, and then put in this 1 kilonewton acting at the 5 meter here. So then you need to cut the section here and here, right? But you will know that here the moment will give you always 0, so you don't bother about this cut section, because 0m, 0 small m multiply big M will get 0 anyway. Okay, just have a try, okay, on this. Okay, maybe we will break for 5 minutes. Okay, then we will proceed on the I have some. Yeah, we will continue with this after the 5 minutes. Okay, we have a break. Okay, so you can refresh your mind first before we get something new about this. Okay. Class, can we continue?
Yes, madam.
Okay. So I hope everyone is here with me right now. Okay, so I'm going to continue with like a consideration. Okay, I would say. Okay, so now this is the title is on support settlement. Okay, the questions here is telling you that what could you relate the support settlement with these two equations below. Okay, so when you have a support settlement, okay, in this case, for example, A and B is fixed, and then at B you have this uh, support have settled. Okay, probably is due to the normally will be due to this soil, okay, performance of the soil, okay, and the whole column may be settled of some magnitude, and your beam supported by the column will also have this deflection. Okay, so what we are going to treat, okay, for our beam, if we already know that this support has settled, sometimes we need to recheck back the performance of the beam, okay, and determine the what is the this deflection once we have known the support settlement. So what you need to do is just to add, after you have determined whatever you have determined earlier from the loading, okay, then you need to add this effect, okay, just plus the delta of the settlement. This delta of settlement, you need to know the value first, okay, before you can put in this equation. So there is two tips for you here. This delta will be positive if the settlement direction is the same, okay, with the virtual load direction, okay, and it will be negative, okay, if the support settlement direction is opposite, okay, with the virtual load direction. Okay, let's have a try. Okay, so just we refer back to example 1. Okay, now we need to determine the deflection B again. Now the support A has settled 10 mm. Okay, so what we need to do is just to add in the effect of this 10 mm here for delta settlement, and we need to go back to the tips. Okay, now support settle is going down, right? Okay, if sometime it will use a uplift or tilt. Tilt is meaning that it will have this angle. Okay, but the uplift is about this uh, upward displacement, or sometimes you'll be saying that horizontally displaced, horizontally going to right, going to left, huh? Something like that. So now this is going down. You know that sector is going downward, and it is same, okay, with what you have assumed your virtual work direction, same direction. So just now our tips is, if same direction, we have a positive delta. Okay, so therefore you use a plus here, then you get the answer right now. Now because of this additional effect as support settlement, we have moved more, okay, downward, okay, of this 10 mm. Okay, so here you can also read and answer my question. Okay, so I would like to go to determine the this for frame. Okay, this displacement, rotational displacement. Okay, we are going to use the second equations about theta. Okay, to get the theta. At where? At point C. So actually the analysis or the procedure is similar like the beam. Okay, we are still using the MM over EI integration. Okay, but now there will be some um, different because we want to determine the theta instead of delta. So look at this. This will be your real structure. We can determine again the this is a statically determinate frame. Okay. Okay, so from here, we are going to have more space, maybe. Okay, for me to. Let's start with solving the real structure or big M. Okay, in this case, we have two members, member AB, member BC. So as mentioned, we need to cut at least once, okay, in this member. So we cut once at AB and one at BC. Okay, then there is no differential loading in within that member, so you just need to cut once. Okay, you need to be able to write the range. Okay, probably I will talk about CB first. Okay, so as a starter, I will use the methods writing the equations. It's the same actually. So, but I will draw the free body diagram here. Okay, so if you can see that this is the free body diagram. Okay, for CB. Okay, where I start my X here. Okay, and I only want to know the moment. Okay, so I have this 5 kilonewton. Oops. So now this 5 kilonewton you need to resolve, okay, into perpendicular to the system. So it has been drawn here. Okay, so now you need to know the angles. So you can see that this T30 is actually here 30. Okay, so 5 is it 30? 5 cos 30. It's not.
Sign is
Since 30.
yeah, sign.
Yes, but where is the 30? Let me check again. Maybe I draw it myself here. Oh, 30 is not here. 30 is here. Okay. So sorry about this. Okay, 30 is here. Okay, so this is 30 is here. Okay, 30 is not here. 30 is here. Oh, I cannot see the arrow here. 30 is here. Okay, so now you have this, knowing that 30 is here, you want to resolve into perpendicular. So it is 5 sine 30. Okay, you get the 2.5 here. So to get this moment done, okay, you can write equation summation moment equal to 0, putting it as clockwise as positive. So now you have m and you have 2.5, and the distance to the x here is 2.5x, and it is okay also acting clockwise, right? So you have plus here, okay, equal to 0. So now you know that m is equal to negative 2.5x. Okay, if you want to go back to my the earlier mentions, directly skip this. Okay, directly write it here. Okay, so how to see from this system. So because this 5 sine 30 is 2.5, okay, it is acting the same direction with your moment, right? Same direction with your moment. Therefore, you just put a negative here. M equal to negative 2.5x. Okay, so now you have solved for your big M, and then you can go to this cut section at AB. Okay, so now at AB, still it is using the X start from B. Therefore, it is considering the whole system like this. You may put in your notes lah. 5 kilonewton. Okay, they are cutting the right section, not the left section, because they don't want to determine the AX, AY, and MA. Okay, so therefore, this is your moment. Okay, now you need to know this 5 kilonewton, what is the distance to x, and it should be measured perpendicular. Okay, so how to get that? You need to solve this geometry. So you know that this is 60, right? To get this is 3 sine 60. Okay, to get this width is 3 cos 60. So you can get this 1.5 meter by the trigonometry. So now there is only one lots involved. It will be 5 multiply 1.5. Okay, so to get this moment done, okay, just 5 multiply 1.5. Okay, but now you are already putting to the other side, right? So you need to look at this moment, whether it is the same or opposite with this your internal moment. So it is the same direction. Same direction, you just put a negative here. Okay, so this is how you get it. It will be negative 7.5. Okay, and the range here, be careful. I have told you in my earlier class, the x must be within this the member itself. Okay, therefore you don't start at C, this x. Okay, you should start at the member itself. Okay, so and then parallel with the member. Okay, so you don't start your x vertically like this. No, you start your x parallel with the member. So x1 is from 0 to 3 meter. Okay, and x2 will be from 0 to 2 meter, something like that. Okay, any questions for this?
No.
Okay, so now I'm going to move to the virtual structure. Okay, so for virtual structure, I'm going to erase this. But virtual structure, maybe I no need to erase that. Okay, because so if you can see that now we want to determine the rotational displacement at C, if you still remember what is the value of this. So instead of 1 kilonewton, we apply in terms of moment, 1 kilonewton meter. Class, do you get that?
No, madam.
Okay, if you want to determine the vertical or horizontal displacement in terms of delta V or delta X, where the displacement is in either vertical direction or horizontal direction, they move for that point. We use 1 kilonewton for, or 1 Newton, the unit will follow whatever in the real structure. Uh, to the point and with the direction of this translation. Okay, but if you want to get the rotational displacement, okay, we apply in terms of moment. We apply virtual moment, okay, with 1 kilonewton meter, either clockwise or counterclockwise. Are you okay now?
Yes.
Yes.
Okay.
So if you can see that now we are not determining the vertical or horizontal displacement, but rotation. So when you see rotation, we need to apply moment, a virtual moment. Where? At point C. So, but now you might ask, I shall put the clockwise or counterclockwise. It's up to you. It's your assumption. Okay, your answer will let you know whether your assumption is correct or not. Okay, so now if you look at this, we still cut the same section. Remember, our cut section for the virtual structure must be same with the real structure. Okay, so whatever we cut just now, we cut at the same place, and then the x start at the same. Okay, with your real structure. Okay, and then your direction of your internal force shall be the same with your real structure as well. Okay, so if I'm going to get my small m1, okay, so I will decide on my right part of this structure. This will be my right part. Okay, the left part I will not, it will be hidden, okay, from my side. Okay, I can't see it at all. Okay, so now I will be looking at any moments or applied load that will be contribute moment to X. There will be only 1 kilonewton meter. Okay, so therefore my M is equal to 1. And then I will check the sign, okay, whether it is positive or negative. If it is, my tips is, if it is same direction, it is negative. If it is positive, if it is opposite direction, it will be positive. So now I get my answer. My small m is -1. Okay. So then I look at this cut section M2. Then I also consider the right section. Okay. So now again, along this section, I only have this 1 kilonewton meter. And it is already in terms of moment. I do not need to calculate, multiply with distance. Therefore, my M2 is still equal to 1. And then I check my direction. This applied moment is same direction with my internal moment, same. So it is negative. Okay. So again, I get my small m value. So what next is to apply the equation. Okay, the equation is not much different. Okay, it is still m over ei, but now there are more member. So what you need to do, you just need to sum out member by member. Okay, so now you need to put in theta instead of delta. Okay, so small m, so you've put the first one is CB, this is CB, this is BA. Okay, you can put in the details lah. This is -1, okay, negative 2.5x. Okay, this is -1, this is negative 7.5. And this EI, if you think that you do not want to put into your calculation of integration, you can put outside. Okay, 1 over EI and integration of so on. Okay, and then the units is in radian. Any questions, class? Now you already get your answer for the rotational. May I know whether this is clockwise or counterclockwise? The theta C. Maybe we need to look back. This is positive value. So
Clockwise.
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 Yes. What you have assumed, your virtual moment is clockwise. If you get a positive value, meaning that you can put a conclusion here. This is actually rotate in such. Okay. Any question for me? Because yeah, I think this is what I would like to share with you this morning. I hope to get any, if you don't understand anything, just ask me now. Okay. I open to Q&A. Yes.
How to get 1.5 meter?
How to get 1.5 meter? 1.5 meter. I think you are asking this. Is it? Are you asking this?
Yes.
Okay. So it is, you can resolve this dimension similarly to resolve these forces. So if you can see that, you can put this into your triangle. Okay, trigo. Okay, principle. Sorry, extent. So this, you know that this is 3 meter. This is 60 degree. So now you don't know what is this y and what is this x. Just use back this trigonometry, trigo principle to get the y. Okay, when you resolve away, so meaning that you are putting it straight, right? Just like your forces, you use 3 sine 60. Okay, so to make it, horizontally, where you putting it close to your angles, right? So you use 3 cos 60. So that is why you get a 1.5 here. Betul ke? 3 cos 60. Let me check. 3 cos 60. Yes, 1.5. Do you understand now?
Okay, madam.
Any other question?
No, madam. So far, so good.
Okay, so if you think that you have understand this lecture, I want you to have a trial on the exercise. Okay, I have prepared many exercises, but I think we can try one first together. Okay, I will be here with you. Okay, for maybe let's say let's to I will see your progress anyway. Okay, I'll be here answering your questions. Okay, let's try this. Will it be difficult? Maybe let's see. How about this? Oh, you choose which one you want. Then it come more and more members. Which one you want? Exercise 1, 2, or 3?
3.
3.
Mm.
Okay, come. Now let's try before we discuss together. Can you try it now? I give you let's say 5 minutes. Okay, then we will have a starting to discuss. Okay, so please do it as fast as you can. Okay, so don't go out from the class yet because we are going to have a short discussion later. Okay, yeah, I'll be here. If you cannot start any, we would I will just help here. Okay, for those who are unable to see this, I think I will crop and put it in our. What we create. Okay, Ahmad Arif.
Yes, madam.
Yeah, are you okay with the question?
Yeah, I'm doing it.
Okay. Amira Husna.
Yeah, madam.
Any question from you?
No, madam.
Oh, okay, good. Okay. Fatin Nabila,
Yes, madam.
you have any question for me?
Belum lagi, not yet, madam.
Oh, okay, okay. So I don't disturb you, Okay. So let's go back to this exercise.
Madam,
Yes,
we should find the reaction first, right? At A and C.
it depends on where you want to start your X. Okay. I suppose you need two. Okay.
Okay.
Yeah, maybe I can show. I do not know where you start your X. Maybe I can show this. This is what I would like to show you later. Okay. You can follow my X direction or you may use your own. Okay, there is no problem. So when I want to start my X1 from A, so I need to determine my support reaction at A.
Okay, madam.
Is there missing something here?
Theta.
I think I missed something here, but I couldn't remember. The maybe it's 4:45.
Theta, madam.
Yeah, I think it's 45. Yeah, 45. 45. Theta is 45. I hope. Sorry, it's 45 degree. Where I get this exercise from? Yes, 45. Do you get this? CY?
Yes, madam. I got it.
Okay. Okay, this is for big M. Okay, so for small m, have you get your CY and AY for big M? Because I want to change my patch already. At 0.3, 2.5, let me draw it here. At 0.3, 2.5.
Madam,
Huh?
my AY I got negative, madam.
Negative, huh? Let me check again. 6, 7.5 minus 8.3. Really? How about the rest?
Positive.
Positive, huh? Yeah. Maybe please check your sign of convention first. Okay. 8.3, 2.5. CY 8.3. CY 8.3. This one is 2.5. Okay. So next, I want to find my small m. If you have proceed, you just proceed, no problem. Small m, support reaction. Oops, this small m has big problem. I forget to take out my lots. I hope you draw correctly. Okay, what I want to determine, horizontal deflection at C, correct? Okay. So now, so my AX, AY, AX, my summation FX equal to 0. My AX will be equal to 1 kilonewton going this direction. My summation moment here. Do you get your CY for your virtual structure like this? Zero 0.309. Right? 2.1除以 1.8 加 2.121 0.554 0.541. Thank you. So this will be 0.541. AY also 0.541 but going downward. Okay. So if you get this, so CY is upward 0.541. This is downward 0.541. This is going 1 here. And then I need to remove this. Okay. And Okay. So, then you solve for your internal force. Let me check whether this is correct. This is x1. Okay. This is for AB. Okay, this is for AB. This is for BC. Okay. 0 to 3, correct? So you need to resolve your forces that perpendicular to your system. This 2.5 kilonewton. Okay, and also this 0.541 in 1. Okay. Oops. Oops. For those who have already obtained the delta HC, just let me know. Maybe you can leave the class earlier. Immediately put it here. 2.5, 2.48 cos theta. Okay, multiply x. This is correct. Okay, opposite, positive, correct. So this is negative 0.541 cos 45 x, negative, correct, plus 1 cos or sin theta, no problem, x one, okay, sin 45. cos 45. Okay, I would prefer here use the sine. Okay, this one I would prefer use sine, but I think they are using the other theta. Okay, so okay, because it's 45, I have no problem with that. Okay, now the next 0.452451 x2. Okay, correct. This is 8.3 x2, correct, and minus 6 times x4 x2, correct. Okay, so I think this no problem, this statement, but the calculation maybe you need to help me. Okay, so how about your progress? Where are you right now? Oh, very serious. Anyone would like to leave the class earlier?
No, madam.
Not yet. How about Adam? Adam Aisamuddin? Have you done?
No, madam.
Where are you right now? Which step are you in right now? Are you able to resolve the process?
Maybe.
Maybe. Okay, any questions here for me? Where shall I explain in further? Anyone? Because we have only another 5 minutes left. But I have checked all these equations here that I have earlier right. It's okay. Okay, and but I did not put in my calculator whether this is okay. I suppose should be fine. Okay, any of you need me to explain on you start at somewhere and you want me to explain the steps?
Yes.
Where?
At the visual force, madam.
Visual force, support reaction.
Boleh lah. I think I got stuck there.
Support reaction.
Hmm.
Okay, mana dia support reaction? Here. Okay, so if you look at this virtual structure, remember there is no 6 kilonewton per meter. Dah keluarkan ke? You need to draw this. So this virtual structure should not have this 6 kilonewton per meter. Okay, but it have virtual load 1 kilonewton acting horizontally at C because we want to determine the horizontal displacement. So now I hope I change my pen. Yeah, it's already in blue. Okay, maybe in purple. Okay, so now I'm looking at only virtual structure. Okay, so I need to put in all my unknown AY, AX, CY. So I start at summation fx equal to 0 here because I already know that only my AX and 1 kilonewton involved in this structure. So AX, I know that it must be acting opposite with my 1 kilonewton. Okay, so therefore AX is 1 kilonewton acting to the left. Are you okay with that? You get this?
Yes.
Okay, so summation MA equal to 0. So now I only have this 1 kilonewton as well. So I need to know what is the perpendicular distance to A. Okay, so I know that this is 45 degree. So to get the vertical distance, I need to put 3 sine 45. That sine 45 or cos 45, you get the same answer. Okay, this is 2.121 meter. Okay, so therefore 1 multiplied 2.121, okay, is your clockwise. Okay, so and then CY is counterclockwise. I directly dump it to my opposite equations. So I have a cy multiply with the length. The length here, you need to know what is the length of this AB, right? So just now, we already know that to get the vertical 3 sine 45. To get the horizontal is 3 cos 45. Okay, still you get the 2.121 meter. So the cy, the distance to A is 2.121 plus 1.8. Okay, so this is how you form your equations here. That's all, because only one unit load. So you can get your cy is 0.541. Can you get it right now?
Yes, madam, I got it.
Yeah, okay. So then you take the last step is the summation Fy lah, because it's only left your Ay and Cy. So Ay must be equal to Cy by acting oppositely. So therefore Ay is also 0.541, but now acting at the downward side. Okay. So maybe because this is the end of the class. Okay. Probably you can take down the solution. Snap down the solution, and you can ask me question later through WhatsApp also can. Okay, or next class. Okay, before we start the lecture. Okay, next class lecture will be on three hinge arch. Okay, so I will share with you on how to determine the deflection of three hinge arch. Okay, but there is no or abnormal things happen. It is still okay a bending type of structure. We are going to determine the bending moment as well. Okay, for the three hinge arch. Okay, so but be prepared. I want you to also go to the I discuss. Okay. I just want to get the feedback from you. Do you get stressed of my previous I discuss questions? Class? Hi. Because this I discuss question is additional so that you can practice, because after you understand the lecture you want to apply it. So I purposely create some these learning activities for you to try on. But I'm worried that it will you have a problem in doing that, or you're getting stressed, because I didn't get any feedback and even the question from you, and maybe I can get some feedback from you. Shall I reduce the question, or shall I put more question? Shall I maintain the I discuss exercise?
Yes, madam, you could maintain, but
Okay.
maybe you could reduce a bit.
Reduce a bit. Okay,
Just a
so
bit.
reduce a
agree.
bit. Okay, so actually, previously my class, they have to do all the question, but in week 2, I think that I worry that you might get stressed because of this ODL, but this is no more reason. Okay, I have asked you to just put any two, solve any two of the question. Okay, but and this week 3, I also include some of the question. I think just try as much as possible. Okay, unless I ask you to submit. Okay, but now I will make it open. Of course, I wish you to try, okay, and get more knowledge by yourself, being trying, practicing, and I also try my best to create my video, my own, to explain, okay. But it take me quite long time for that, because I need to make sure the slides there is no problem, and and playing about this technology. And this week I managed to do one only for you. Okay, it will be on the internal hinge. Okay, maybe you can go through this. I discuss this, redo this exercise step by step as what I have shown you in the video. Okay, I hope it helped you. Okay, so if you don't have any more question, I will keep continue with this I discuss problem, but I won't enforce that you must finish all the question, but at least you need to post some of these in our forum. If not, when I monitor, your name is not going out. Okay, from my I discuss, maybe I will consider you as a passive student. Okay, I may want to call you. What happened? Do you have any problem? Okay, so if there is nothing, I will stop recording. Okay, and then I see you next class. Okay,
Okay,
bye
madam.
bye.
Thank you,
On
madam.
arts, madam.
Yeah.
Okay, thank you, madam.
Okay, bye.
Thank you,
Bye.
madam. Bye,
Thank you,
madam.
madam.
Thank you, madam.
Thank you, doktor.
Kenapa kau sedih sangat
Thank you,
semalam?
madam.